Okay, good morning everybody. So I'd like to report some new results which we've generated recently. So we've been using quite sophisticated techniques to fingerprint soil carbon under different soil carbon amendment regimes. So kind of I feel the current context for the work is against the 4 per mil initiative. So I'll just briefly begin by introducing this. So this is basically an initiative pushed by the French at the Conference of Parties in 2015, and really the kind of fundamental idea behind 4 per mil is that if you were to increase soil carbon stocks globally by 0.4%, so 4 per mil every year, there'd be sufficient carbon sequestration to offset the anthropogenic carbon emissions. In a nutshell, that's the idea. Of course, globally increasing soil carbon everywhere by 0.4% every year is a large challenge, and how you might go about doing that with land use change or amendments is very much up for exploration. Okay, so I'm going to report information for 2 studies. The first of those is a field experiment, a plot experiment, which uses inorganic fertilizers, addition of sewage sludge, and addition of chicken manure as carbon amendments in the soil system. And the second study relates to the use of biochar towards the same ends. So in these experiments, we're basically asking 2 fairly fundamental, straightforward questions. So the first of those is, how do those additions alter the carbon stocks? But more importantly, how do they alter the recalcitrance or the lability of those carbon stocks? And then secondly, the question is, well, if we're presented with various options, which option might we pick to try and achieve this 4 per mil ambition? Okay, so we've been probing the diversity of dissolved organic matter molecules, and to do this we've been using a sort of relatively new technique, which is Fourier transform ion cyclone resonance mass spectrometry. So what this is all about is basically a carbon fingerprint, if you like. So for a long time we've had DNA profiles. We can interrogate microbial communities in the soil, work out which members comprise that community structure, and to report that biodiversity and functional performance. This is a new approach which basically stems from proteomics. So proteins are complicated and they are in the environment as mixtures. That is analytically a challenge to deal with. But this particular kit, this FT-ICRMS, has been an established method to look at those proteins. Now, more recently, people are thinking, if it works with proteins, why can't we profile dissolved organic matter molecules using the same approach? So, kind of a brief history of everything, beginning with the Korean alphabet and moving forwards. We've had various tools to look at soil carbon along the way. So, size exclusion chromatography gives a feel for the molecular size of the organic molecules which are in a sample. Moving forwards in time into spectral characteristics, so emission excitation spectra to look at the chemical functionality. NMR, more recently still, again providing more information on functional groups. And now, very far into the diagram, use of FT-ICRMS to look at individual DOM molecules. So what we're seeing here with time is a move from broad scale appreciation of the carbon molecules to much smaller scale. And with that, we're going from low resolution to much higher resolution in what we're looking at. Spectrum out like this, and each spike on here a unique DOM molecule. So what we do with this data, conceptually, is then to take the information and put it onto one of these Van Prevalent diagrams where the OC ratio and the HC ratio are cross-plotted against each other. But what's significant here is that each one of these dots is a different molecule. Okay, so you've actually characterized each of the molecules which are on the diagram. What we can then do with a bit of conceptualization is to define different parts on the diagram. So things which got a high HC ratio and a range of OC ratios at the top of the diagram are aliphatic molecules. And as we move down through the zones, we then have unsaturated phenolic compounds, we've got polyphenols, and then finally our very condensed polyaromatics. So depending on where an individual molecule arrives, we can start to think about what is its fundamental properties. Is it quite degradable, or is it quite recalcitrant? We can, of course, bulk all the data together and look at different sort of major groups, so CHNO molecules, CHO molecules, CHOS molecules. What's important here, as a distinction though, is that this isn't a bulk sample. This is a percentage of the molecules which fall into those categories. So we're actually, with high precision and resolution, defining the chemical characteristics of the DOM. The other diagram just kind of relates to the zoning that I just went through. And again, we can look at percentage of unique molecules which fall into different categories. Right. Okay, so that's kind of a complicated view. What I'm going to do today is simplify things and just use this line 1.5, the HC ratio of 1.5, to differentiate molecules which are relatively labile and degradable against molecules that are more recalcitrant. Polyphenols, the condensed aromatics, those sorts of molecules. Okay, so there's two studies. This first study was just got accepted in the S&T, and it basically looks at sewage sludge, chicken manure, and inorganic fertilizer. And it asks the question, how do those amendments change the carbon stocks, and how do they change the recalcitrance or lability of that carbon? Fairly simple experiment, just a randomized block, where we're adding fertilizer, so we've got 2 additions, recommended dose and a half dose, chicken manure, sewage sludge at 1, 2, and 4 times application rates, replicate diagram. What's significant is the experiment's been conducted over 10 years. Every year an addition has been made. And we're now looking longer term at how the soil carbon has responded. Okay, so the first piece of data on here, and what we can see is that high application rates of sewage sludge, these ones up here, increased TOC and increased DOC within the systems. In contrast to that, if we look at the inorganic fertilizer treatments, you see no change in the carbon stocks, maybe slightly decreasing much, and no real change in the DOM. If we then take this forward and look for unique molecules within the sample, what we see emerging are really quite distinct groups. Okay, so we've got yellow over here, it's chicken manure, red, sewage sludge, blue is the inorganic fertilizer, and the green are the control soils. So again, just to remind you, the top part is our labile molecules, and the bottom part is the recalcitrant molecules. So what we basically see is that the inorganic treatments, they basically coincide with where the control profile lies. But then as we start to move to unique molecules which are in the sewage sludge treatments, they're moving to a more recalcitrant part of the diagram. And then if we move finally to the chicken manure, it's moving further in that more recalcitrant direction. What we then did for this paper, the S&T paper, was to look at the microbial community structure. So of course those two things link. The DOM and the resource, the DOM resource, of course, underpins the microbial diversity within the system. It's just a little bit of sequencing of bacterial 16S DNA, and you see these community profiles, which I'm not really going to explore in any detail. But what we did was then to undertake a network analysis, to ask the question, how do the DOM molecules link to the microbial community structure? So this is, I suppose, is the original part of what we've done with the analysis. We've not only characterized the molecules and the community, we've tried to establish how they link together. Lots of detail on here, but at the bottom, where we ended up is that when we seek for a reasonably strong correlation, we find about 135 correlations persist, linking 40 DOM molecules and 17 of the bacterial taxonomic units. If you look in a bit more detail at the networks themselves, what we see as we move from control to the sludge amending system is this a much more diverse network. You see more linkages, more DOM molecules being linked to the bacterial community structure. And in contrast to that, we then look across the way as we move from the control to the inorganic fertilizer treatment. We see that reduction in the linkages between the nodes of the molecules and the bacterial communities which are represented. In light blue, we've got labile molecules, and in dark blue, we've got recalcitrant molecules. It's not really time to dig into this, but the paper will be out in the S&T soon, can have a further look. Okay, so that's the first study. That's about chicken manure, sewage sludge, and organic fertiliser. The second study is a biochar study. We're currently working on this. I've been in China for a week, working with collaborators. So hopefully we'll get this study out, submitted at least in the next month or so. So this was done in the UK. This is one of our biochar trials. We've got 3 different soils across the field, ranging in texture from loam sand to loam. And we basically set up a random plot experiment with char application that's been incorporated, and then for the last 6 years it's been mixed, equilibrated, weathered, allowed to do this thing. If we look at the data from here, what we basically see is, of course, that put in large amounts of char, so we're applying up to 100 tonnes per hectare, increases our carbon stocks, as you'd expect. But interestingly, over here, we see very little change in the DOC. Okay, so control against 50 tonnes and against 100 tonnes, it's really only a very high application that we're actually seeing a decrease in DOM in 2 of the char-amended soils, but not in the other one. If we then take this forward, have a look at these groupings from these bioprevalent diagrams. Again, you see distinct areas emerging on the diagram. So the first area to point out, of course, is the char itself is recalcitrant carbon. It's down here well below the 1.5 line. And then if you look at the soils and the char-amended soils, well, they've kind of got a mixture. They've got molecules which are quite labile, and molecules which are recalcitrant, some of them very recalcitrant. But we then finally have a look at the soils themselves. So this is the sandiest soil. This one here is the middle texture. This is the loamy soil. And again, we're seeing unique molecules that are emerging in these samples that weren't there before. If we then, of course, do it already, and look at recalcitrant molecules and labile molecules, what we can see is that in the char-amended soils, so these are the 50 and 100 tonne per hectare applications, these are unique molecules that aren't present in the control. So we see obviously an increase in a range, a vast range of recalcitrant molecules, which to my mind serves one particular purpose. It provides carbon storage opportunity. On the other side of the coin, what we see is an increase in labile molecules, the yellow section on here. And this, of course, is important because the labile molecules provide a resource for the microbial populations. So I think the evidence here is slightly different, in so much as we're seeing an increase in both labile and organic molecules. So, conclusions for the 2 studies. I think chicken manure sewage sludge studies suggest that we're seeing an increase in recalcitrant DOM stocks following those additions. And in the biochar studies, we see an increase in both recalcitrant molecules at the bottom and labile molecules at the top of the diagram. And so I would say collectively, my sort of overall conclusion is that probably it might be worthwhile to pursue combined amendments to try and build carbon stocks, but also increase residues which are available for microbial assemblages. And the reason for that is that they hand forward those microbes to provide function within the soil system, and by increasing carbon stocks in a way which feeds that microbial community, we can expect to see better nutrient cycling and better delivery of the ecosystem services. So I think my overall conclusion is that char on its own, manures, organic materials on their own, fine, they serve a benefit, but really we need to think about making those additions together to get the dual benefits of carbon storage on one hand and improving the resource for the microbial communities on the other. Thank you very much. Yeah.
Thank you very much for your wonderful talk. I have a short question. Actually, when you use these such big techniques, normally the molecules goes under changes. Is this technique, do the molecules go under certain changes and they produce some DOCs or DOM which actually don't exist due to breakages or during the measurements? Do you think like that?
That's a possibility. I think the way the data is handled is that we're looking at the shift from the control situation to the amended situation. So if you have those errors, which is what we're getting at, I guess the errors should be even in both, and by making the deduction you are resolving to a large extent that problem.
I actually use IRMS with gas bench using N2. N2 for gases are different a bit, but 30% of N2 is like break it down into NO, and that's effects on the isotopic values in the end.
Yeah.
So this kind of that's why I asked this question. Okay. I have another question. I can ask later. Someone, please. Yeah. Sorry.
In the treatment, in the first half, you presented that the amount of available organic substances in the control increase. How it's possible the increase if you don't bring anything, especially labile carbon, because fiber should be decomposed much faster than the recalcitrant.
So in the first study, there was no real change in the DON. The amount was the same in the control as it was in the inorganic fertilizer.
If you don't bring any organic materials, DON and lipids, especially over 10 years, should decrease.
Yeah, but there's new carbon inputs from the plant residues and exudates, so it's not a closed system.
Okay.
Brian,
Okay, that's right.
very small question. You used term labile molecule and organic molecules. What is difference between them?
So labile I'm using operationally for molecules that have an HC ratio of more than 1.5. So they're all organic molecules.
Okay.
The labile ones, they have this higher H to C ratio, so they're more delicious.
So if I understand that correctly, so when you refer to labile carbon, you are indirectly calling that dissolved organic carbon, or that
So
is different?
all the analysis for DOC
Yeah.
was just the DOC fraction.
Okay.
Good, right. Thank you very much. We'll move on.